taking your three rules. You have a power rule, a product rule, a quotient rule, and a root rule if you want to throw in there before the power in case you have a radical. So they work like exponents. And this is what we look at. If I am multiplying this, 5 times x, it's being multiplied, it's a product. When you multiplied your like bases, you added the exponents. So logs are exponents. So we're going to separate this into an add. And a log base 10, you can put the 10 if you like. You don't have to put the 10. It's base 10 automatically. A division, a quotient rule. Our quotient rule says when you divided like bases, you subtracted the exponents. We turn this guy into a subtract. Everybody good so far? Power rule. This is the one you're going to use the most. You bring the power down in front. When we have a variable in your exponent, that's what's going to help get it down, is the power rule. A root rule. This is my root rule. Before you can bring down your power, you have to get an exponent. So a square root is the same as a half. There's a little index of 2 here and a little 1 here. A cube root is a third. A fourth root is a fourth. Then bring it down. Logs and ln's work the same. You can use ln for anything, but you have to use ln for base e. So if you look in our books that we use here, I don't even think I handed them out in the beginning, right? Said if you wanted one, I could give it to you, but nobody seems to ever want to drag one around. Because you can usually Google and find it easier than looking in the book. But the book is a college level book. Most of the time you'll see them just use ln. Because if everybody is like a universal, they'll just use ln. Okay. We get to expand again. This is a product, y times x times z. So we separate that into an add. This guy we separate into an add, and then we bring the exponent down. Remember, this exponent only belongs to the b. This guy only belongs to the c. You have to separate them before you can bring down their respective exponents. 59, make it into a fraction exponent first. Bring down the exponent, then you have a divide, and separate the divide. This is really important, guys. Watch what happens here. This 1/3 belongs to both of these. If I use my power rule and I go like this, I essentially have x squared over y squared. Both of them get that exponent. So if you wanted to separate it first like this, you absolutely can. You can separate it there first. Or you can do it after your divide. But remember, this has to be in parentheses because it belongs to both of them. Whether you distribute it or not is fine with me. You can leave it outside of it. This guy, this is just a qualifier. Your logs, your domain is greater than 0. But what happens if we put a 0 in here? This guy will be a 0, so it can't use it. But what happens if we put a 1 in here? Then your numerator will be 0, and we can't still take the log of a 0. They've just qualified. It has nothing to do with your working on this. So you're going to expand this. You had a quotient, so separate it into a subtract. Then you took this argument minus this, bring down this guy. If you left it like this, that's perfectly fine. I separated it out in case you did, but there's really no need to separate that out. Because if you're going to plug in for x, you can plug it into this one just as easily. So you can leave it either way. What you don't want to do is separate this argument. There's nothing to separate that argument when it's just 2 terms. Okay. Here's another one. Undo your division first. First undo your division. Change your root to an exponent. Okay. That's a product in your numerator. Now, if it's more comfortable for you, put parentheses around that numerator. Order of operations will perform it in that order. If it was the other way around and that was in your denominator, then you would definitely need parentheses. But because that came in the numerator, you didn't. But if you're more comfortable with it, put parentheses. Keep your numerator grouped. Undo your quotient first. Undo your product. Bring down your powers. Everybody good with that? That's a big one. Can everybody do that one? Okay? Then the next part, you had to condense. You had to condense them. I don't think I gave you 65, right? No, I didn't give you this one. I start from here. So before you could do anything else, get rid of the guy in front of the log work. There's your exponent. Bring your exponent back up, and that's all we could do. Again, this guy, bring your exponent up. If you wanted to, convert it to a radical. Bring your exponent up here first. Then you had to subtract. That made us a quotient. You need to be able to bring that down to one term, because we're going to see that today when we do equations. Again, subtract. Think about when you were subtracting your exponents. Oh, you were dividing your like basis. Bring it back to a divide. Good. The last one is probably the hardest one here. So, oops, not the last one. This guy is a little tougher. Work order of operations. Work from inside. Inside those parentheses says combine those into one. Combine those first. It was a product when I added my exponents. Then look where your 2 is. Your 2 goes on the outside of that whole product. Then you had to subtract. Subtract meant you had a quotient. So I'm fine either way you write this one. You're all good with this. All right, for the next parts, you have to just evaluate them. Did I say algebraically? Did you, you didn't have to do it?
You have the graphs.
You had the graphs up to this? Okay, let's hit the graphs. Let's hit the graphs.
Can you go over how to find the x-intercepts for this logs again?
Yep. Put your y equal to 0. What you're going to end up doing is flipping it back to an exponential equation. We did the first 2, right?
Yep. No. It was 50. Wait, no, we did the first 3.
The first 3. All right. So let's start here. So this is a good place to start. So this guy, when you see this, run your finger from the x being positive to the x being negative. Where's your reflection? Over the y-axis. I want to see reflection in the y-axis. No flip over, just reflection. Now, this causes your domain to switch around. Your domain originally went from 0 to infinity. Now it's going to go from negative infinity and stop at 0. Your asymptote is still in the same place because that was the line of reflection. That's your y-axis. That was your line of reflection. Now to find your new y-intercept, graphically, we know that this point, when it reflects, it goes over here, right? Algebraically, we're going to say, okay, set this guy equal to 0, because isn't this where y is equal to 0? We're just going to take this, log base 10. You're going to flip this back to an exponential equation. If it's easier, reflect this. Do it this way. You can use your back, your base, your answer, your exponent. You can use log equals exponent. Take the base. Remember, this is base 10. To the exponent, that's 0, equals negative x. Anything to the 0 power is 1. And divide by negative 1 to solve for x. And doesn't that confirm what we found graphically? It to confirm what you find rapidly. We didn't have to do a y-intercept because there was no y-intercept. We have an asymptote at your y-axis here. Make sense? Okay. This guy, whether it's ln or log, they work the same. ln is like very close to a base 3. You have a horizontal shift the opposite way. -1, go to the left 1. So now, because you took a horizontal shift, your domain says push it back. 1. There's your new domain. I could take this and algebraically find my domain. Well, I know my domain for logs has to be greater than 0. So if I set this equal, I should be able to find my new domain. My range is not changing. My asymptote, when it was at x equals 0, that got pushed back. So there's my new asymptote. My x-intercept, I could see it now at the 0, 0, right? Because it got moved back 1. Algebraically, plug in a y of 0. Now, this is what looks bad, right? Flip this around first. Log, well, ln equals exponent. What's the base of this log, or this ln? E. It's understood to be e. What's the exponent? Follow the thing. 0 equals x plus 1. So anything to the 0 power again is 1. Subtract 1, and x is 0. It's going to be the same thing when they do a base 10 on you. They don't have to write the base 10. And kids stare at this the most, believe it or not. Same as the ln. They stare at this one too. Where is my base? How am I going to change this? Even a few years back, where is my base? My base is 10. Put the 10. My base is e. Put the e. Makes a big difference if you put it there. Because you can stare at them, and when I see kids confused, it's usually right here. Okay? This one, if you want to switch it around first, negative x plus 3, so you can see your shift going a little bit better, and your reflection. Again, plug in an x, a y of 0. It's an ln, so use your base e over here. E to the 0 equals this. Easiest way to go, guys, is this way. Cover this up. You raise this guy below here, you raise it to the 0 equal to this. And just solve for x. This is 1, and solve for x. Okay. Change your asymptote. Don't forget, a horizontal shift will change your asymptote. So be careful of that. Alright. I think we had one more. I don't know if I can move this. There it goes. Is this the last? Nope. Log base 2. Is everybody okay with that? There's no transformation.
We didn't do that.
We didn't do, oh, you didn't have this either?
We did that in class.
We did this one in class. Okay. Good. So we're good for that? Alright.
You forgot my name.
Oh, I gave it to this row. Did you have extra, Heather?
Yeah, wait.
Yeah.
Caesar.
This is what I wrote.
I said it correctly.
And you have one?
Just about my kids.
Like 20 minutes in and I'm still awake, so I think today might be a good day.
Mine's just big. Did you get pretzel on you?
I got a pen.
Look at that.
I always bring a pen.
All right.
I just don't use it, but I drink.
You have everything you need, Jeremiah? Okay. All right. Now, 3 types of equations. There are 3 types of equations. First type, there's no log words in here. You'll see an exponential equation. We have 2 ways we can solve this guy. We can break them down to the same base, keep them exponential. We can keep it exponential and solve, or we can convert them to logs. Okay? Such as 2 to the x equals 8. So 2 to the x equals 8. I need to know what my exponent is. Now, sometimes I could break this one down into a base of 2, right? Then I could say, okay, x is equal to 3. Now, we also learned a nice little rule that brings down that exponent. It's your power rule, but it's got to say log in front of it. So, second way to do this is, okay, give logs to both sides. If you remember the list of properties that I gave you, where ln and e canceled out, and log of a, 0 equals 1, the whole thing that we gave, the last step said this: if x equals y, then the log of x equals the log of y. So if I have one term on each side, I can apply a log to both sides. And then I can use my power rule and bring down that x. So I can divide both sides by log 2. Now, you can't divide 8 by 2. The log 8 is an identity by itself. The log 2 is its own identity. You have to put in your calculator log 8 divided by log 2. That will also give you the answer of 3. Okay, so we have 2 ways to do that. The second equation is, I have one log word. I'm just making this as simple as possible. So say I have this. The log base 2 of 9 equals x. I can't take that log word away. I can't put a log on the other side because it's an equation. I'd have to put it on both sides. But I certainly don't want to do that. Let me just give a different example. Let me give a better example. Let's make it more reasonable. Let's do this, because you'll see it flip around. So I can't take it away because it's an equal sign. I can't put a log word there because then I'm only changing one side, not the other. So I change this guy to an exponential equation by using my back, or my log equals exponent. What's the base of my log? 2. What's my exponent? 3. Oh, look at that. And I solve it. I didn't want to do this, the other one, because you could put that in your calculator to solve that anyway with your log base. So I wanted to give you one that will actually, we could see. The third way is every term is log. Has a log word in it. For instance, the log of x minus the log of x plus 1 equals the log of 4. Now, I cannot just take all my log words away until I condense this and make it one term equals one term. And then I can go back to this rule up here and take away my logs. So what was I doing when we subtracted? You were dividing. So you're going to condense this and make it divide. Now, this is one term, one term. Now you can take your logs away. Then you can cross multiply and you can solve. Now, we always want to go back and check. As long as you condense this down to one log statement, and you have one term, the same as your rule, you can take the logs away.
Oh.
When it's one term. But here's the biggest difference. If everybody doesn't have a log, you can't do that. You have to do number 2 way. You have to isolate it and flip it around to an exponential one. So there's really only 3 kinds, no matter how bad they look. And the thing to remember is ln works the same way as log does. That I could do ln's for all of those instead of logs. They work the exact same way because it is a log. It's just a natural log. So we see the 3 types? Good so far? All right. So I need to get rid of all of this. Let me start again here. All right. Now we're going to look at our 3 types. So this guy, I'm going to rewrite this like this. Isn't e a base of my exponent? Isn't 2 a base of my exponent? So does it matter which base I use? Could I even use 3? Aren't they all going to work the same? Right? So when we had this condition, we said, could I drop this down? Could I drop 72 down to a base of 2? Try. Try 2 to the 5th, 2 to the 6th, 2 to the 7th. Do you hit 72? No. So we need to get that exponent down. Your power rule pulls that exponent down. But it's a power log rule. So we're going to put the log of both sides. So I can use log or ln. So I'm going to take ln of both sides. Same thing over here. I'm going to take the ln of both sides because with the e, I have to use ln. I could say log over here, but I'm just saying ln. I could say log here too. So they all work the same, right? It's just with e, you have to use ln. So now I can apply your power rule and pull this exponent down. And I can pull this exponent down. Now this one's nice because you have this nice little property that says ln and e cancel each other out. They're inverses of each other. They cancel each other out. Not in this case. In this case, we have to divide both sides by log 3, or log 2, or ln2. But this one has a nice little property with the ln and the e. And then I'm just left like this. Now, if I need an exact value, this is my exact value, or I could go to my calculator and do 3 decimals. So 3 decimals gives me what? Thank you. Now, it's an equation. Can I check this? So let me take e and raise it to this. I will be approximately 72. I say not exactly because I rounded. Right? We're close enough. If I took my exact value and I put it here, well, e and ln cancel out. So isn't 72 equal to 72? So that was our first condition, right? The first one. We had no log words. No log words in there at all. This one has no log words in there at all either. So I need to get it to one term. I need to isolate my exponents so that I can do exactly what we did up here. So what should I do first? I need to get this by itself. Subtract 5. Now doesn't it look like the other one? Remember, e is a base, just like a base 2. If I I want to get that exponent down, I have a nice power log rule, but I need to have those word logs there. I have an equal sign, so what I do to one side, I have to do to the other. Since it's a base E, I have to say ln. The ln's are nice with the base E. What happens to my ln E? First of all, my exponent comes down, and this crosses out. Out this comes. Ready? A log doesn't work that way. We saw with the 2 and the 3 in there, we had to just divide by that. But an ln works nicely. Okay, now this third one, again, has no log word in it. It has an exponent, so I know I have to use a log to get it down. But I have to isolate it first. What do I have to do to this 4? Good. Divide by 4. Now, I have a bunch of different ways you can do this. We can kind of do that, divide by 4. I'm just going to leave it 5 over 4. I got to get my exponent down. So what do I have to do next? ln. ln of both sides. I'm just going to leave 5 over 4. I bring down this entire exponent. What happens to my ln E? Cancels out. So how do I solve for x? Divide by 2. Now, we have another way we could have done this. We kind of cheated a little bit. But this guy was a product, wasn't this? So it's still one term, isn't it? My left side, isn't it still one term? So if I took the ln of both sides, that's still okay because it's one term. And I have a product. Oh, don't I have a product rule that says separate these? Can I do this as well? Legally, that's what I probably should do because it's a one term. I bring this down, only belongs to the E, don't forget. And the ln and E is going to cancel out. I got to subtract ln 4 from both sides. Now remember, you can't subtract 5 minus 4 because it's attached to the ln. You have to say ln 5 minus ln 4 and then divide by 2. Make sure you put this in parentheses when you do this. It'll come out to the exact same answer. Legally, that's the right way to do it. Could we cheat and just divide as long as we don't round anywhere and leave it and round to the very end? We're okay. So just kind of a couple of ways you could do that. Are we good with this one? All right, let's hit the next time. The next time we have one log word here. I'm going to do this at the same time. I'm going to stick a log in here. I'm going to do them both at the same time. Aren't they the same expression? This one has an actual log, one has a base 2 log. Okay. Let's work the right side. What would I do to the right one first? I take away the 5. I got to isolate this guy. I got one log word. I can't cross it out. I can't add a log anywhere else. Okay. Now what? Divide by 2. Yep. Let's get rid of it. No, now what am I going to do? Back. Okay, base, exponent. I'm not really sure which way you do this, but this way. Just go like this and come around. Can I do that in my calc? Mm-hmm. What do we get? Point, I'm sorry? 707. Thank you. Okay, I can go back and check it. Can I plug that in here? Put this in my calc and make sure it's close to 4. Remember, it's not going to be exactly because we round. Okay? Same problem over here. It's the same exact problem. Can I subtract 5?
Yeah, what happened?
I'm sorry. I'm subtracting 5. What am I doing?
What happened to the log?
Well, we had to get rid of it, but we couldn't get rid of the log when it's on one side. We can't automatically cancel it out because it's an equal sign. We can't put it on the other side because we'd have to put it again on this side. So when you have one log, you're going to flip that to an exponential equation.
Oh, and then it just drops since you switch it?
Then when we got rid of it, we took your log equals exponent or back, whatever you use to convert it. And this is going to be the same thing. Now, I got to get this out of here too. What's the base? I saw my base here. I don't see my base here. What is my base? E. Okay. Same exact thing, isn't it? No, because I'm a different, you changed your base a little bit different. But you're pretty close. What answer did you get for this guy? 606.606. But because, don't forget, this guy's closer to a base 3. So the answer is a little bit off, but the process is still the same, right? Okay. The last one we have is the crazy one. I have logs everywhere. Everywhere. So my goal is condense them to where it says log equals log. Alright? What do I do for this guy?
Multiply them.
Multiply. When I was adding my exponents, I was multiplying my like bases. This time around, we're going to move this guy up. Ha! How many terms is this on the left-hand side? One term. Two products, one term. How many terms on my right-hand side? One term. If you are one term, and they both have logs, you can take the logs away. It's an equal sign. You're doing it to both sides. It's no different than if I had this. I'm dividing both sides by 2. I'm taking that factor of 2 out of there. So long as I'm doing it to both sides. Now, I'm left without my log statement. And yeah, you have to work this whole thing out. So, 2x squared minus 3x minus 4x plus 6. How do I solve this? It's a quadratic. What do I have to do? Get everything to one side. Set it to 0. Very good. Subtract x squared. Okay, and factor. My signs are both negative. When my signs are the same, I'm on factors of 6 that add up to the middle.
X minus 6 x minus 1.
Good. So therefore, x is equal to 1 and x is equal to 6. Now, I need to check those guys. I have to make sure that I'll never take a log of a 0 or a negative. So I come up here. And the same thing when you work with radicals or absolute values. I put a 1 in here. What happens when I do 1 minus 2? Negative. I can't take the log of a negative number. So I have to say reject. Let me test my 6. 6 minus 2, 4. I can take the log of 4. 6 times 2 is 12 minus 3. I can take the log of 9. Log of 6, I could do that one. So I can keep that one, and then maybe you further want to check to make sure that that works.
Yeah, it works.
That one works, right? But always make sure, and don't automatically discount it if it is a negative, because sometimes it could say this. ln x plus 3, and it could be another one, like ln x squared. So if your answer is negative, your negative could still work. So don't discount it if your value is negative. Try them. Be sure that you try both of them. As you note